Shankar, who will tell us about, so it's kind of a bit of a change in topic. So Shankar will tell us about a local automaton for the toric code. Yeah, please take it away.
Thanks. Thank you. Yeah, so I'm going to talk about local automaton for the toric code. It's with Margarita Davidova, who's at Caltech, and Ethan, who's at Berkeley. And we also want to thank Peter Gach for many helpful discussions. Okay, so brief introduction and motivation. Guess I don't need to talk about this in too much depth, but we're interested in storing quantum information in a noisy environment, right? In order to build a reliable quantum computer, we need it to be robust against effects like noise, which are caused by coupling the systems to some environment. So that's maybe a computer science motivation, and maybe a way of phrasing this more formally is you take some circuit or some computation that you want to perform, and then you encode your information redundantly in some large number of degrees of freedom, say n. So it could be qubits, could be other things. And when we're performing the computation, we're able to run for an amount of time that's exponential in n. And even in the presence of noise, when the system is coupled to the environment, we should be able to recover the original quantum state with high probability. So that's maybe for the CS audience. For the physics audience, there is a motivation which goes under the broad purview of dynamical quantum phases, right? So if we take some phase of matter like a superconductor, right? The superconductor is constantly interacting with the environment, but somehow it still has measurable properties that allow it to deem it a superconductor. So there's some sense in which some phases of matter are stable in a dynamical sense. They're able to survive even when constantly being bombarded by the environment. So this is kind of an interesting question from the physics perspective. And maybe a formal way of talking about this is, let's say that we have some generic Lindbladian, L, and the Lindbladian is targeting a certain density matrix. So the density matrix might be a state at finite temperature. It also might be a state caused by applying a very shallow depth circuit of noise to it. And we want this Lindbladian to be kind of dynamically stable. So as we add noise to the system, we want this fixed point state to not be changed too much. So these are the two different perspectives of thinking about why storing information robustly is important. So, okay. But we'd also want to add other requirements from physics, right? And the requirements in particular concern locality. So we live in, 3 spatial dimensions as far as we know. And so therefore, when we're building a sort of Lindbladian or a quantum circuit that encodes information robustly, we would want all of the elementary operations to be local, geometrically local. We also not want to cheat by making classical operations non-local. So when we're doing some quantum operation and we have to send a classical bit across the system, we'd want to take into account the amount of time it takes to propagate classical information by some distance. Right? So we want to take kind of speed limits into account. So that's illustrated here. And last, we'd also want to be below 4 dimensions. Right? So these are some reasonable requirements. Maybe they're not completely practical, but they're a good theoretical requirement to impose. Right? The other requirement, which was kind of implicit, was to impose what we call robustness. Robustness is just the same as fault tolerance, right? And the model we're going to study is that we take a particular circuit and we assume that some noise has occurred in space-time somewhere. So this just means we have some probability distribution describing the noise. We sample from that distribution, and this gives us a bunch of locations in space-time. And we assume that we can change what these operations are in a completely adversarial way, but only change these operations that obtained from our sample. So we'd want this kind of property that even under the presence of this kind of noise, if the probability of noise is low enough, we should be able to properly decode the state. Right? And we want this robustness not only in terms of the quantum bits, so the qubits present in this procedure or dynamics, but also in any kind of classical procedures that we're using as well. So this is again, maybe a reasonable requirement. Maybe it's not completely practical, but from a theory standpoint, yeah.
Sorry, I missed your beginning. But so apologize. But these are you're describing conditions for fault tolerance, or
we're just
general conditions for fault tolerance.
We're just describing conditions that we want to impose, maybe from like the physics perspective. So maybe from the physics perspective.
But for what? For achieving
fault tolerance. Yeah, that's right. So yeah, and from now on, we're going to be dealing with a certain kind of noise model, which is often called the local stochastic noise model. And this is kind of what I've described. You have a probability distribution over a set of locations in space-time. And the probability that a set A is chosen, so the set of red kind of things, is less than p to the power of the size of the set. So basically, it's some slight generalization of things like IID noise. And it captures things like exponentially decaying correlations. Okay, so how do we achieve this? A natural starting point is just to use different models of fault-tolerant quantum computers, right? Because we know that this is kind of what we want to achieve in the end. So assuming these particular requirements of locality and speed limits, how do our current models fare? So the first kind of model that showed a threshold for quantum computation was due to concatenated codes. And it was by Aronov and Ben-Or in the late 90s. And it can be shown through some more work that concatenated codes satisfy all of the desired properties that we want, right? They can be made quantumly local and classically local and completely robust. But unfortunately, there's no other current construction that we know of where we can achieve this, right? Where we can make all of our operations local and still preserve the memory property. Yeah?
So I thought Aronov and Ben-Or that they allowed long-range classical communication.
They do, but then there was some subsequent work by Gottesman that tried to address the locality of this.
Is that the local?
Yeah. Yes, that's right.
Yeah, that's classically local.
Yes. But I feel like it would be nice to kind of write out the entire argument, like with all the details.
I don't think you'd get that just from reading his paper, so if that's what you're asking.
Yeah.
I think Aronov and Art, they don't need non-local classical communication. Gottesman's contribution was the 1D.
That's right.
Yeah.
Gottesman's contribution was making it in 1D, but.
Sorry, yeah, my understanding was Aronov Ben-Or did not need any classical computation at all. They just did it entirely quantumly and locally.
Yes.
I thought there were others that did it using classical computation, but I thought that those were local.
My understanding, you mean there are other different constructions?
There were other constructions that achieved fault tolerance, but they assumed that they had perfect classical computers, or classical computers don't really know how to achieve fault tolerance there, right?
A lot of these constructions assume that there's some amount of classical non-locality, basically. So either like the classical operations were not local, or you make certain assumptions that classical computation was performed very rapidly over a period in time. So these constructions, people don't quite know how to make them completely scalable for this reason. Yeah. So this talk we're going to focus on topological quantum computation, and I'm going to explain why some of the current constructions are not scalable as per this definition. Yeah, scalable simply means all quantum operations are local, classical operations are local, finite speed limits for classical computation and communication, obviously being below 4 dimensions, and being completely stable against both quantum noise in space-time and classical noise. So all of these are not achieved for various reasons in these models like topological quantum computation. So in topological quantum computation, finding a solution would entail finding something that's called a local decoder, and so this has been, a problem that has been open for some time, and to
Finite density of degrees of freedom.
Yeah, that's right. So here's the paradigmatic way that 2D and 3D topological memories work, right? So what you usually do is you do syndrome measurements. You can do syndrome measurements pretty easily by measuring local parity checks. And you store measurements for an extensive amount of time in the space-time volume, basically. So this means you store them for an amount of time that's order the distance of the code. And oftentimes then you process these syndromes using a non-local classical algorithm. So you use some kind of minimum weight matching algorithm, but this algorithm relies on the fact that you need some global information about all of the syndromes, and then you're operating globally on that. Right? So it's not, and then you'd have to feed back the results. And this feedback can occur with a delay, and all of these three things turn out to be an issue in order to make things scalable. Because you need to remember measurement outcomes for a large amount of time, and there's no way you can remember for a large amount of time without non-local storage of information. You need to process these, and you cannot process these. All the classical algorithms available to us are not local, or at least if you were to make them a local circuit, they wouldn't be fault tolerant against noise. And the feedback can also occur with a delay, and you'd have to take this into account. Yeah?
Can you say again why the first two things are L cubed and not log L? I would think that if I have a bunch of syndromes and I need to match them up, I'll only need to work for log L. That's the longest thing I should typically.
Yeah, this is mainly for if you want to store things for an exponential amount of time, say. Because then to scale it up, you just make your toric code patches log size. And in order to do a polynomial computation, you need to make your toric code patches log size, use many of them, and you would need some scaling like this.
That part again. But it's log in space-time volume, right?
This is the other part, right?
And the time is really long, right?
Yeah. So based on these conditions, it's not scalable, and it's not what one might call a dynamical phase of matter. So here's maybe a practical reason we'd be interested in this. Our goals are purely conceptual. Like a lot of our assumptions are not necessarily needed, but some ideas would be useful practically, and this is because Google has kind of found that when they need a decoder which has this property that it's a real-time decoder, right? So the decoder needs to keep up with the device, because otherwise, if we just have to wait for the decoder to do its operation, things can slow down, and you no longer are able to get scalability. So this is a question of practical interest as well as theoretical, even though some of our assumptions are rather strong and maybe not practically important. Okay, so what are the possible approaches that we can use to build such a memory? So the first approach, which was related to the talks in the morning, were to just take some Hamiltonian system and just put it in a bath and the bath has very low temperature. And just hope that you by just allowing the system to evolve under its thermalizing dynamics, the content would be preserved, and this would be called self-correction. The second way to do things is to build a device specifically like a refrigerator. So you would put your quantum computer in a refrigerator, and then the refrigerator is always dumping entropy out into the environment in some active way, and you essentially hope to preserve your quantum state this way. So this is what one might call fault tolerance. So fault tolerance is going to be the model that we're going to be dealing with, and we're not going to be talking about self-correction. But it's good to review kind of the state of things in both fault tolerance context and the classical context when we impose locality. So for classical memory, we know that in one dimension, there's no classical memory. That's because of various physics results, like the 1D Ising model does not have a phase transition. So you can't construct some 1D classical Hamiltonian which can encode information. In 2 dimensions, you might think that the 2D Ising model is an example. But one of the issues with the 2D Ising model is if you add a longitudinal field, so basically if you add a z term to the Ising model that tries to force one of the ground states to be all up or all down, then you suddenly lose the ability to store information in the all up and all down configuration. So 2D is currently, it's not known because of this. And in 3D, there is an example, although there's no rigorous proof. And this example is due to something called the Wegner, or also sometimes called the Ising gauge theory. Yeah, so, yes?
For 2D, I didn't quite follow your argument. Are you saying that the Ising model doesn't work, or Watt's model would also not work? Or
just the Ising model itself would work, but then we'd also want the Hamiltonian to be stable under perturbation. So let's say that I were to apply like a magnetic field to the system that tries to force all the spins to me. Yeah.
Yeah,
So
but then are you saying that that's true for the Ising model, or in general for the Potts model or other models in 2D? Nothing's known.
Nothing's known. Yes, because the physics reason is if you have something called spontaneous symmetry breaking, then it's essentially not going to work. And all of these models, like this Potts model and Ising model, they all have this property.
I see.
But you avoid this property in 3 dimensions. Yeah. Okay. So is there an example of a classical memory that doesn't use dynamics where you thermalize with the environment, but make some active local decisions? Right. So one example is something called Thom's rule, and it's an example in 2 dimensions, and it has the following very interesting property. So in the fault tolerance concept, the way we're going to model the noise is at each point in space-time, we flip a bit with some probability p. That's what would be called unbiased noise. It's called unbiased noise because if you're a 0, you flip to 1 with the same probability as if you're a 1, you flip to a 0. But you can create a bias. You can have different probabilities of flipping from 0 to 1 and from 1 to 0. And that bias plays the same role as this kind of longitudinal field in this 2D Ising example. But remarkably, Thom's rule is stable to both unbiased noise as well as biased noise. And the reason why it works is, first of all, it doesn't need to satisfy something like detailed balance because you're not doing something like Glauber dynamics. And the other reason why it works is because if you can see, like, domains of flipped spins get eroded in kind of an asymmetric way. So you might ask, is there hope that because in 1D there's not even an ordered phase in the classical model, is there even hope that we can use a local rule like a cellular automaton rule to stabilize a active quantum memory, a memory actively? And the answer is yes. And and there's this very long history, but there's a proposal by Peter Gotch back in the 1980s who constructed an extremely complicated model which appeared to be an active memory and completely stable against arbitrary noise. But not only this, his model turned out to be a universal computer, so it can do very complicated, arbitrarily Turing-complete computations. And on top of this, it can store information at a finite rate. So the number of encoded bits is not just a single bit, like in the Ising model, but order L bits, where L is the size of the system. Yeah. Sorry, I mean arbitrary noise with respect that satisfies this local stochastic error model that back in the first or second slide. No, not like adversarial noise or something. Yeah. Yeah. There's actually a way you can easily destroy the Tomes rule memory with adversarial noise. Yes, and there's a simpler construction which doesn't have all the bells and whistles of Gotch's construction, and this is due to Cyrilson. And Cyrilson's construction preserves a single bit of information in one dimension, but the star means that it's not translation invariant in space or time. So the rule that you apply is different depending on the location. So now let's go to the quantum setting, and this is where our results going to come in. So in the passive case, I'll go through this quickly since we had 2 talks on this already. But in 2 dimensions, saying it's impossible is a bit of a stretch, but under a certain kind of model, which are stabilizer CSS Hamiltonians, Aliski et al. Kind of provided a good argument that it's not possible to have a passive memory in 2 dimensions. In 4 dimensions, there's the 40 toric code, which we heard a lot about. And in 3 dimensions, it's an open question. How about in the active case? Well, in 4 dimensions, what we can do is we can construct a local rule. And what the local rule does is it stabilizes the code space of the 40 toric code. And the way it stabilizes the code space of the 40 toric code is by using 2-dimensional classical rules, so Tomes rule. And the reason for this is that if I look at excited excitations in the 40 toric code, they look like membranes or loops. So these kind of figuratively look like the 2-dimensional domain walls in the 2-dimensional Ising model. So you might think that a rule in 2 dimensions might stabilize the 40 toric code. The answer turns out to be, indeed, this is possible. But to my knowledge, there's not been a construction providing a cellular automaton or active decoder for any topological order, any topological code below 4 dimensions. And one reason for this is that in 2 dimensions, so in 4 dimensions, we kind of know that we need a 2-dimensional classical rule for the x and the z sector. So in 2D, so there's this like dimension doubling kind of phenomenon that happens. So then in 2D, we can extrapolate and say, okay, if we have a 1D classical rule to correct the x and z sectors, we might be able to stabilize the 2D memory. Unfortunately, all 1D classical rules that we know of, which are completely robust, are extremely complicated. And this is, in some sense, why it's been so hard to solve this problem. This is the candidates. The first one is this very complicated construction. The second one is the simpler construction. And what we do in our paper is we use this simpler construction to construct a automaton or decoder for the 2D toric code. But it's not a translation invariant rule in space-time. So I'm applying a different rule at different points in space-time.
Sorry, can I have
Yeah.
clarification?
Sure.
So when you talk about like the passive case, like how you model the local mass, it's like you apply mass to each side?
Yeah, I mean, there are some kind of standard ways of modeling it. It's a little complicated, but like in the classical setting, so in the quantum setting, it's a little complicated, but in the classical setting, you can use something like Glauber dynamics. Okay. So basically, I locally like flip a spin with some probability depending on the energy cost.
Okay, and then we modeled for the active decoder.
It's just a cellular automaton rule. So the Tomes rule is actually very simple. It's I have a particular kind of cell, and I look at itself, its north neighbor, and its east neighbor, and then I take the majority of the three, and then I update that cell based on those values. So it's like it's just a local update rule.
Yeah, and maybe my question is about like how you define the locality is more about this particular site operation, but for different site operation, do you assume they need to have commute or they can overlap or?
So we assume that they shouldn't overlap. So because you should be able to kind of implement them kind of simultaneously. Right, so they shouldn't overlap because otherwise they interfere with each other.
Though they overlap, they can still.
Yeah, if they commute, then that's fine. Okay. But the way we're going to construct things, essentially we're going to construct it's going to look like a circuit model in some sense, and so at each layer of the circuit, the gates don't overlap. But
okay, so it's like partition of all that.
Yeah.
Okay, thank you.
Yeah. So maybe I'll skip this part, but there's been kind of an interesting history to this paper by Gatch. It's been a very complicated construction, and in fact, the referee for the paper wrote a reader's guide to it. And the reader's guide to it is like 50 pages long, and the paper itself is like 200 or more than 200 pages long. But Cyrilson's automaton is much simpler. It preserves the code state of just a simple classical repetition code. And it doesn't require something like an enormous number of states per site. So it's something that we can more easily reason with. It actually provides some simple principles that underlie why Gatch's more complicated construction works. So our results are, as I mentioned, we construct a local kind of what we call measurement and feedback circuit, where we just measure the stabilizers of the toric code locally and then apply some correction operation. The way it's going to work is, I'm going to use the word hierarchical, but you should also think about RG, or Ling renormalization group, if you're a physicist. The amount of time that we can maintain the encoded state for is exponentially long in the power of the system size. And it is a local fault-tolerant memory, and for the physicist, you can think about it as a dynamical phase of matter. But as I mentioned, the rule that you apply is going to be different at every point in space and time. Breaking the space translation symmetry is not too bad, but the time part is a little problematic, and we can fix this by moving to 3 dimensions. So the construction that works at the end of the day is a 3-dimensional construction based on a stack of 2D toric codes. And this slide is just to emphasize that there were other attempts, one by Harrington, but Harrington suffered from multiple problems that doesn't make it completely local or scalable in the sense that our construction does. Okay, so now I want to talk about Cyrilson's automaton. For computer scientists, you can just think about this as a construction based on concatenating classical repetition codes. I'm going to overview this. So as I mentioned, the way Cyrilson's automaton works is it preserves the code states of the 1D repetition code in the presence of noise. And why do we want to consider something like this? Well, it's a good starting point because what we want to do is we want to correct errors in the 1D Ising model or the 1D repetition code. And you can think of errors or syndromes as being points, basically. The points just correspond to locations where the value of the parity check is 1. Or the value of zi times zi plus 1 is -1. So you can think about correcting a configuration as basically a sequence of points on a 1D line, and you want to kind of merge these points together. Because if I take 2 points and merge them together, they basically get kind of annihilated. But you want to make sure you do this in the right way. Because suppose here I have kind of a domain of kind of spins which got flipped. And let's say I have 2 points at the end of the domain. If I annihilate the domain by going around on the opposite direction of this 1D line, assume it's in a circle, then I would completely change the code state. So I would need to be careful about how exactly I do this procedure of merging these 2 points. And in the toric, this is important because in the toric code, again, the syndromes look like points. And we're going to be doing something more complicated in order to stabilize the toric code. But it's going to be, inspiration is going to be taken from this example. OK, so the main idea in Searlson's automaton is you just introduce a small number of what we call elementary gadgets, and you write down substitution rules, where you build bigger gadgets by substituting in these smaller elementary gadgets. So here's how it looks like, right? As like a carrot catcher, right? Like you have these 2 different prototiles, and then you build bigger and bigger tiles by gluing together these prototiles. So as a disclaimer, we're going to just discuss a modification of it, which makes it more transparently similar to concatenated codes. So the gadgets are just going to be 3 different gadgets. There's going to be a gadget that looks like this. This just means what we call idle. So basically, the bottom point is the value of the bit at some time t. The top point is the value of this same bit at time t plus 1. So this just means I don't do anything to this bit. This means I take 2 bits as input, and I swap their values. And finally, this gadget is called the majority gadget. It takes 3 bits as input. It computes their majority, and then it broadcasts the majority, think about it as like a fan out, into these 3 output bits, basically. So that's, and this gadget is going to be responsible for error correction. But the error correction is done locally. So here's the slight modification of how this works. We're going to take these gadgets, which we call level 0 gadgets, and then build level 1 gadgets out of them. So the way we're constructing this is simply that this level 1 gadget is built out of just a sequence of level 0 gadgets. So sequence of idles and idles here, sequence of idles and swaps here, sequence of idles, swaps, and majority here. And this kind of recursion relation, we simply just iterate at higher and higher and higher scales. So to formalize it, if C is, say, some circuits, basically, this is the circuit that we want to encode into this bigger code, we're going to define what's called a fault-tolerant encoding of this circuit. So the way the fault-tolerant encoding of this circuit works is we take each bit of the circuit, and we replace the bit with three bits, basically. So we just enlarge the circuit by a factor of 3. We then replace every x0, y0, and z0 in the circuit with a fault-tolerant version of them, constructed from this recursion relation. And then between each application of the x1, y1, and z1 gate, we insert a layer of z0 or error correction between that goes across the entire system. And Searlson's automaton can simply be thought of as iterating this process some number of times n, where n is roughly the log of the number of bits you start with. So here's how this looks like. So suppose this was our circuit that we want to encode. We run the fault-tolerant procedure once, you get something like this. Then you run the fault-tolerant procedure another time, and you get something like even more complicated. So one interesting thing that we can do is we can just see if I apply an error somewhere in this circuit, like a domain of bits I flip, like what does this do? How does this propagate? So you can see that it propagates in a fractal-like structure. So in particular, in the reason why, say, this fault-tolerant procedure works is if I have a domain of spins that I've flipped here, what they do is they get fragmented into 3 kind of separate channels, and these channels get isolated from one another. And then the recursion continues to iterate, basically. So these segments will get split and further separate, and this keeps repeating until the segments are small enough that they can just be directly corrected by an error correction or majority unit. So that's what happens here, right? They split and isolate, and then here, since we've done the recursion twice, they split and isolate once more, and then they just get directly corrected. And this is not just, so this is assuming I've made an error in the input. But again, as I mentioned in the beginning, this also works if I have in the presence of transient noise. So that just means if I have noise that occurs at other points in the space-time, it will still properly clean up this domain of flipped bits. So that's a very important property that this should have. So the theorem that Cyrilson proved for his version of the automaton, which is slightly different than this one, is that if I start off with a state of the bits, which is all ones, and then I run the automaton for t time steps, and then I run a procedure which is called decoding, D. And D just computes a global majority of the configuration because the code states are all zeros or all ones. Then the probability that if I started with all ones, the decoded state will be 1, is greater than or equal to 1 minus t to something that's exponentially small in power of L. And that's essentially the statement that shows that this is a memory that lives for exponential time. Because t can be exponentially large, and the probability that the decoding would work out is still going to be 1 minus epsilon for some small epsilon. So this is a statement that we'd want to prove. And of course, the proof is more sophisticated than what I'm going to say, but an intuition for the proof is, in quotes, reverse the arrows. So what does this mean, basically? This means that all we're going to do is we're going to start off. Let's suppose we have an error here that occurs like at this point. What we're going to do is we're going to identify the larger gadget in which it occurs, and we're going to say that this error causes an error, say, in this larger gadget. Well, since we've done the fault-tolerant simulation some number of times, this larger gadget, if we undo the simulation, looks like a smaller, a level 0 gadget within a smaller level gadget, basically. So what we've done is we've identified the location in which this gadget fails. So if I have a cluster of errors, I identify all the gadgets within which this cluster of errors occurs. All of those errors fail. And then I propagate that, or undo one level of the recursion, and say, OK, this gadget must have failed. And I keep repeating this until you just have a single gadget which fails within a larger gadget. And if you can somehow prove that your gadgets are constructed so that they can clean up single gadget failures, then you've been able to prove that fault tolerance property. So this is obviously a very, very sketch of the proof. The formal proof uses a method called the extended rectangle formalism that was first developed by Eleferis, Gottesman, and Preskel in the mid-2000s. Okay, so that's a kind of a lightning overview on how Cyrilson's construction works, and it's essentially just concatenated repetition codes, again, for the computer science people. So how do we use this to construct a quantum kind of automaton for the toric code? So first, we have to kind of convert to a more quantum language, right? So we know that in Cyrilson's automaton, we're really working with bits. We can kind of measure or read out the value of a bit because it's a classical variable, right? But we can't really measure or read out the value of just a single qubit because that will destroy the state in the quantum context. So instead, what we're going to do is we're going to convert this model into what we call a measurement and feedback model. So this just means that since Searlson's construction operates with the classical repetition code, let's rewrite each of these elementary gates as measuring stabilizers of a classical repetition code and applying a certain Pauli feedback. So you can do this for the idle gate. And so for the idle gate, it's pretty trivial. You don't need to really do anything. For the swap gate, it turns out that you can perform this 2-qubit swap gate by measuring a parity check of the classical repetition code and applying a Pauli feedback, which is x tensor x on the 2 bits. So you can just work that out and see it works. And it turns out for the majority vote, you can also interpret it this way. You can measure parity checks of the repetition code and apply a Pauli operator feedback, and that will simulate the action of the majority vote.
Sorry, now it's a majority vote on what?
Sorry, you can think about this as a majority vote plus broadcasting, right?
No, but for the quantum one,
yeah.
We're measuring 3 syndromes?
No, here you're measuring 2 syndromes, and then you're applying Pauli feedback on 3 bits. So yeah, I should have made this clear, but the bits are now on the edges of this.
What are we trying to do with the qubits on the edges?
Yeah. Okay. Good. So what we're trying to do is all I'm trying to do is rewrite these gates in terms of making a measurement of a stabilizer, and then applying a feedback, which is a Pauli operator, because this is all completely classical. But in order to go to the quantum context, because the toric code will be measuring stabilizers and applying Pauli feedback, in order to go to that case, you need to reformulate something like this in terms of this language.
I guess I'm asking what O is.
I'm going to describe that. Okay. Yeah, thanks. Yeah.
Is it the same as saying that you want to come up with an operator that will linearly apply the majority vote, so that if you feed it some superposition, it will maintain the superposition, but do
yes.
majority vote in each?
Yes, that's right. Yeah, so you want an operator O that essentially does something. So here's how the majority vote is going to look like. Right? So what this operator O is going to do is, if you have 2 points or 2 syndromes, that means this bit is flipped relative to these other bits. And the majority vote is going to clean up, basically, like flip this middle bit back, right? So this operator should just take these 2 points and kind of annihilate them. Otherwise, if there aren't 2 syndromes kind of in the middle, what the majority vote should do is it should do a procedure which we call coarse graining. It should send the syndrome to the boundary of these 3 of the 3 bits. So that's what this operation is doing. It basically does error correction if you have 2 syndromes that are very close to each other, and then it does this coarse graining procedure otherwise. And after applying basically, say, a layer of majority gates to the system, the syndromes will now lie on what we call 1 vertices. So they'll lie on like vertices at every 3 sites because of this coarse graining property. Right? You can think about this from the bit perspective as your code words here are going to be all zeros or all ones on these 3 bits, and so the domain walls can only occur at every 3 sites. And what is this operator O? Well, it turns out because for the case of the toric code, we need to choose a slightly different basis of gadgets. So we introduce the same swap gadget, which we call T now. But now we're going to introduce a gadget which we call M. M is just a simple gadget that's going to take 2 syndromes and is going to match them. So it's M for matching. So if there are 2 syndromes, it's going to annihilate the 2 syndromes. And otherwise, it's not going to do anything. Then you can write the majority voting type operator as this sequence of M and T operators. So yeah, so this should answer your question. Okay, so now that we've kind of interpreted things more in the context of measuring stabilizers and applying Pauli feedback, let's also look at another aspect of Searlson's automaton. What I'm going to claim is that Searlson's automaton does a dynamical version of coarse graining. Right? What does this mean, basically? At each level of the simulation, syndromes, which are like very close to each other, turn out to get annihilated, basically. That's important in order to do the error correction. And otherwise, the syndromes move to these coarse grain sites. So at like level 1, the syndromes which are like 1 away from each other get annihilated, and syndromes which are slightly farther away from that just get coarse grained to the nearest sites. And Searlson's automaton operates by just doing this process self-similarly. So at the next level, 2 syndromes which are neighboring level 1 sites will get annihilated, and otherwise they'd be moved to the level 2 sites. So this is what I'm going to call dynamical coarse graining, or maybe dynamical renormalization group. And we want a similar analogy in the toric code, want a 2-dimensional version of this. So to do that,
just be clear, if I wanted to do this without Searlson's things, would I need log L time at the last step? Is that the trouble with this?
you would need not actually log L, you would actually need order L time. Because if you'd want to, suppose you're at the highest level, then the distance between syndromes is order L. So actually, if you want to move them and then annihilate them, you need order L time. And you don't actually want to move them by level 0 operations. So I'm actually going to get to this point. Yeah, so to do this, you can think about this as you construct things 0 cells and 1 cells. So 0 cells are just 1 by 1 cells. 1 cells are 3 by 3. And one thing to keep in mind is that for those of you who are kind of familiar with concatenated codes, there's this notion of code blocks, basically. So you have, like for concatenated codes, you have multiple code blocks, and you can construct a new code somehow by combining these code blocks at one level. And you can kind of think about this patch of 3 by 3 cells as like a code block, even though you shouldn't interpret the toric code as a concatenated code. So you can go on and construct these blocks at higher and higher levels. And so we would call these K cells. And you can also construct the boundaries of these blocks at some levels. And we call these 1 frames, 2 frames, and so on. So here's one attempt of how to construct a local rule, which is recursively generated for the toric code. So one way to do it is, suppose you have a configuration of errors, and these cause a configuration of syndromes, which are these black dots. So what we do is we look at syndromes which are kind of very close to one another, and we clean them up. And then for syndromes which are slightly farther away from each other, we coarse grain them so that they're located at the sites of the 1 frame. So like this. And using this concatenation analogy, you can think about the code words of this code as basically different configurations of syndromes located at corners of this 3 by 3 block. So then we just recurse, basically. We repeat this procedure. Now we can go to the next level. We look at and see whether syndromes are very close to each other at the next level. And if they're very close to each other, we get rid of them. Otherwise, we coarse grain them, like this. And then at this last level, these 2 syndromes get annihilated. Okay, so this seems like a good procedure. So I explained to you how you should annihilate syndromes and if they're too close to each other, and then coarse grain them otherwise. Why can't we just, yes?
So the coarse graining, I was more confused by that, but you sort of move the syndrome over to sort of the closest something.
Yeah. So basically, like at level k, you have points which are like distance 3 to the k away, and then you just move it to the closest kind of point. Yeah. So, why can't we just take these syndromes and just apply like local quantum operations like swaps and just kind of move them around, and that would be something that's local and would work. Well, this turns out not to work. There are 2 issues with this. The first issue is that there are certain kinds of configurations where if you don't apply this RG scheme properly, will just grow uncontrollably. So basically, if I have like an error that occurs right near the boundary of like of a higher cell, then that error can actually grow. So this point can be sent to this point, and this point can be sent to that point. And because that error will keep growing and growing and growing, it will prevent the system from being a quantum. It will essentially proliferate. The other issue is that if you try to move these points by just applying like little swap operators, the swap operators are not reliable themselves, right? They fail with some probability p. So you're not going to be able to send the defect to the desired place because with probability, so some fraction p of the swaps that are needed to send this point to this point are going to be completely corrupted. So instead, what you have to do is you have to build reliable kind of swaps or reliable gadgets which can move things in a reliable way. And this can only be done by using a recursive procedure similar to Cyril's.
So can I push again on
Yeah.
issue 2? So
Yes.
if I'm below threshold, then I think that once I've got to scale L, I have exponentially small number of syndromes remaining anyway. Right, so typical longest strings I'll have.
That's right. But even if you're not at the largest scale, you'll still, like, suppose you're at scale where the distance between the anyons is log L, then you still won't be properly coarse graining them to the right points. Because also, like, in order for this procedure to work, like, you will have operations at some level which are conditioned on the location of an anion or a syndrome here. And if you just have one error, the syndrome is not going to make it to that point. And so you're going to be conditioning on like the wrong value of the syndrome, basically. So it's a very like fragile process if you just use like level 0 gadgets to kind of move defects. Yeah. So the way this is going to work is now using this measurement and feedback picture, we can construct versions of these gadgets that work for the toric code. And the way it works is, we measure the stabilizer of the toric code, and then we apply local Pauli feedback. So in this case, we're applying local Pauli feedback x tensor x. And same with the match. We measure if there's a syndrome here and here, and then we apply a Pauli feedback, which is x at this length. And then we also have the same versions of these gadgets, except they're applying feedback in a vertically oriented fashion. And similarly, in 1D, we have a gadget that does this coarse graining procedure. So I'm not going to discuss how this gadget works because it's like operates in like 48 steps. So if you really want to know, ask me at the end, and I can explain why it works. And then what you can do is you can just kind of do something similar to what happens in Cyril's, and you can similarly construct these gadgets using a substitution rule. So now I'm going to construct this gadget at a higher level using this circuit of lower level gadgets, and this gadget at a higher level using this circuit of lower level gadgets. And the fault tolerant procedure is going to work very similarly. Like, we take our toric code, we increase it by a factor of 3, we replace each level 0 gadget with level 1 gadget, and then between each level 1 gadget, we tile the lattice with these error correction units, and that's how we're going to construct this circuit. So here's just a quick demonstration of how this works and some particular input of syndromes, basically. So the red lines just correspond to, say, the errors that created the syndromes. So we would say that the system got corrected if either the red lines completely disappear or if the red lines form loops, because the loops just mean that you applied a stabilizer, so you're in the stabilizer. There we go. So as you can see, like, there's this process in which, like, these syndromes are like branching and splitting, essentially. Like, they're branching out and they're kind of splitting, and then because this procedure is very inefficient, they kind of come back and recombine. But that's simply just because we may not have the most efficient way of doing of designing the gadgets. But essentially, what you're going to find is this branching and splitting process occurs at all levels, and eventually these errors get corrected. It just takes a long time. So the threshold is not very large, but the fact that a threshold occurs is the important part. Yeah. So the way the fault tolerance works is morally very similar to how it worked in the Cyrilson case. It's just there's an additional subtlety, which is you would hope, at least with concatenated codes, if you go up one level in the simulation, you'd be able to correct a single level gadget failure. What ends up happening here is that if you go up one level in the simulation, there are certain kinds of single qubit errors which don't get corrected. So you actually have to go up some constant number of levels in the simulation in order to get the desired error suppression. So error suppression meaning p goes to p squared. So in order to so because of this, because of going up some constant number of levels, so k is some large constant. We showed that it's like less than 34, but it's not particularly important what the number is. If you go up some number of levels n, the error suppression goes like p to the 2 to the n over k, and this simply implies that we'll have a memory that lives for an amount of time that's exponential in some power of the size of the system. Just that the power can be very small. So this is the high-level sketch of the proof, but maybe I'll defer this if there are any detailed questions about the ideas. Yeah. So finally, the last thing I wanted to mention is that because this construction, the operations that you're applying, although they're local, they depend on space-time. They're different at each point in time. One might complain that this is not completely local, because in order to specify what operation you're performing at a particular point in time, you need a memory. And the memory has to have an instruction set which is of size log L. So, but the important part is it's a read-only memory. What this means is you created this memory a long time ago. You applied all the operations in this memory. You never need to change the memory. You don't need to write to memory, and you'll still be fault tolerant. So because it's a read-only memory, you can actually turn this two-dimensional construction into a three-dimensional construction, where now all the operations are local. There's no time dependence, but it is not translationally invariant in space. Yeah.
If you could use the translation invariant one, this would have not.
This would not. Yeah, exactly. And what the problem there is that you essentially just need to find a way to just use an order one number of bits to specify this instruction set, because this instruction set is a very special structure. So it might be possible to compress this into, and that's kind of the idea that Gotch used. So yeah, so I want to end on some interesting open questions. So now that there is some three-dimensional topological quantum memory which is local, can we do this for other kinds of codes like non-abelian anyons or fracton codes? The thing I'm interested in is finding a quantum version of Gotch's automaton, which has a lot more kind of interesting properties like translation invariance, implementability in continuous time, constant encoding rate, so on and so forth. Gotch's construction also has this interesting property of self-organization. So what would this look like in the quantum setting? And finally, is it possible to use this construction to perform things like universal quantum computation? So performing Clifford gates may not be too hard, but performing the non-Clifford gate might be an interesting task. So I have to stop. Yeah.
The very last point about universal quantum computation. Do you mean performing non-Clifford gates still in the toric code, but
still in the toric code? Yeah.
Like how?
My understanding is there's a paper coming out tonight on this. Yeah. But not done locally, basically. So the goal is to find a local rule that does it. But this paper that'll be coming out tonight that is able to do it in 2 dimensions, basically, by using switching to some non-abelian topological order, performing the transversal gate there, and then switching back. Yeah.
What do you mean by self-organization?
Yeah, it's good. What is essentially just meant by self-organization is just the ability to perform like arbitrarily kind of complicated procedures, like even the presence of noise, basically. Basically, the ability to create structure from kind of almost nothing. And because that's kind of what's needed in order to perform like a computation. You need to create the structure that provides the program that allows you to do the computation. So what does this really mean? Yeah.
Can you expand on the comment that you need to go k levels up to like see the...
Yeah. Great. Okay. I guess I'm just going to go over this. I'm going to go over all of this. But this is kind of how our error correction gadget works. So there's like a very particular error, which because of the design of our gadget, what ends up happening is it grows. But so you can see that this error is, I'll call this like a diagonal error because it has one syndrome here and the other syndrome on the other diagonal point. What it does is after one level of simulation, it becomes an error where the syndromes are on these 2 points. It seems like it grows, but it turns out that this error in one higher level is a correctable error, basically. So the idea is that as long as after a constant number of simulations, the full set of errors eventually turn into a set of errors that can be corrected, then you can still prove fault tolerance.
Is this any different than saying, let me define a new gadget, which is just 2 levels?
Yeah, it's not. And the way we talk about it in our paper is simply by doing that. Yeah, it's just almost impossible to first of all, you need to figure out how many levels you go up, and that's like a completely different. That's kind of complicated. So we couldn't have ever constructed these gadgets by like just doing a search over some much larger thing. So. Yeah.
Maybe just coming more from a more practical perspective of this. You see there's a connection from this to really doing more efficient decoding of quantum memory, and also you have in your final slides you said there's some desiderata for what you're looking for. I assume those are like the sense with nice physical property, and you can have physical meaning. It's more like a sufficient condition for having a practical use for decoders. But my question is maybe for the reverse direction. If I have something maybe have some efficient property in practical decoding, but not having all the property you're looking for here, do you think there's a way to connect that back to physics? Or how what are the the physics required requirement here that you think some kind of codes where it has physical meaning?
It's a good question. I think if you're thinking about practical matters, oftentimes you don't care that, you don't care about the classical computer needing to be reliable, because we know that classical computers are exceptionally reliable. You also can make the assumption that classical computers operate much more quickly than the quantum computers can operate. So these are like the additional assumptions that come in when you're addressing practical things. I don't really know if there's any deep connections to physics to physical models per se, but I certainly think that it's worth thinking about these things. And
maybe I can give you some examples.
Yeah.
I think right now this is related to my first question. So right now you're basically doing all the decoding, really helping on disjoint sense, and they don't really share any communication.
Yeah, that's right.
And that definitely will be a perfect case for doing decoding. You basically localize all the computation. You don't need to move the information around, which is something really hard to do in experiments.
Yeah.
But in the case that you assume there's some very little communication happen, that would be better than you need
Yes,
the global information to do the the decoding, right? So if you allow that to happen, do you think there's a way to interpret that, with some physical meaning?
Yeah, I think there's maybe the question you're getting for is if you were to like violate this like the speed limits, like how good can your fault tolerant protocols be if like you start to not impose that like precise speed limits, like classical information can propagate from this point to this point like at some particular rate, but like so we're always assuming that it travels at some finite speed, but like maybe it travels at speed like log of the system size. Then like how much better can you make your fault tolerance? Like yes, these are interesting questions. I don't quite know yet how interesting they are in the like perspective of like physics or fundamental physics, but like they're definitely like interesting kind of mathematical questions you might ask.
Okay, thanks.
Okay, are there any more questions?
This idea of taking one extra spatial dimension to get like one-sided invariance, like time translation invariance, but not space. Do you know if Hannah Bernard could do that?
It's a good question. I think it's possible that you can do it with their construction, but
feels like hard to work out, I guess.
I mean, maybe it's not too hard, but yeah, you would probably need to think a bit about the subtleties because the codes are non-local. So that's why you need certain circuits in order to fault tolerantly measure stabilizers and stuff. So you need to see how that works in the layering construction. But I don't think it should be a problem.
Okay, let's thank Shankar again, and let's also thank all speakers of today. And we now have a tea time, which is upstairs on the second floor, and then there's also like lots of whiteboards to keep on discussing.